droplet, and the out is by convective heat transfer, and the value of H is provided. We also do not have any generation of heat in here, and as a result of this loss, some amount of heat is going to get depleted. So there would be a depletion of this in here. Now, rho is a function of temperature, and we obviously, if rho is a function of temperature, then V and A could be also a function of temperature, but we keep them for the first generation approximation, we keep them to be a constant. So we define a new theta, and we write the governing equation. Now the governing equation with the temperature dependent term embedded in here. So what we have then, this theta is nothing but the temperature difference, and this is a compact equation which I should be able to integrate the way I can see it. And we know that at time t equal to 0, the theta is simply going to be whatever be the temperature of the droplet when it is in contact with the heater. I think it's provided as to be 350 or something. And T minus T infinity, the T infinity is the temperature of the colored yellow liquid. So that is also known to you. So we could integrate this in order to obtain the temperature, the time needed for the temperature, the relation between the transient temperature and time. So that's the governing equation. So you plug in the numbers in here, and but we need to realize that this is probably another part is the polymer will start to fall when its density is equal to that of the colored liquid. The trick is that it doesn't have to be at the same temperature. Okay. So even though the polymer, that means the sphere, hasn't reached the same temperature as that of the surrounding fluid, yellow fluid, it can still fall because its density is now equal to the density of the colored liquid. So thermal equilibrium may not have to be achieved in order for the droplet to start its downward journey. So the temperature, it calculates the temperature at which the densities are going to be equal, and then you would see that the theta 0 to be equal to 25 degrees centigrade. Initial value of the temperature difference between the droplet when it starts its upward journey is 25, and when it starts its downward journey, which I call as theta reversal, so it should be 330 minus 325, I think, is the temperature of the yellow one. And then you could, you know all the values, so you could put everything in there and find the temperature to be about 500 seconds. So it would take about 500 seconds, close to maybe 8 minutes or 8.5 minutes for the droplet to slowly rise through the top, and multiple droplets are going to rise one after the other, and number of droplets will also come down. So at a steady state, the droplet motion through these colored liquids with a backlight would be extremely pleasing to the eye, and it's kind of a soothing, relaxing environment that it creates. So, do you have any question on this?
Do we assume constant velocity of the rise of the sphere?
Yes, right. There is another assumption. So what we but that assumption is not as restrictive as the assumption where we say that the volume and the area remains constant. So what we say is that the terminal velocity, in this case, the upward terminal velocity of the droplet reaches very quickly, and which is quite small in comparison to the 500 seconds, the final result that we have obtained. So that's another assumption. But I would expect that if the viscosities are quite high, then the distance over which the velocity increases from 0 at the bottom to a constant velocity would not be significant in comparison to the total time. But you are correct that yes, that is an assumption which we have to keep in mind. Any other question? Okay, then we will move on to a problem which is different. It is not a transient problem, and I did not include any problem from Hasselhoff chart. Are you aware of this? Or do you know about this Hasselhoff chart and how to read them? Yes or no? In transient conduction, what to do if the Biot number is greater than 0.1? How do you handle such cases? I'm sure you have studied that in your heat transfer class, but since conceptually it's the same, except that solution methodology is slightly different, so it's more like the specific method to be used for solving such a situation without any additional physical understanding to be incorporated. So I'll skip that part and move on to a different problem. So this is more like a traditional chemical engineering problem in which the concept of the simultaneous convective and conductive flow of heat, as well as the amount of heat generated by a specific reaction, is to be taken into account. So what you see is the reactor. It's a reactor. Okay. So the reactor is from 0 to L, and the reactor contains a number of catalyst particles which are present in here. So the catalyst particles, so this is at Z equals 0, and the reaction ends at Z equals L, because the catalyst particles are only present between 0 to L. But there are a number, there is a region before the start of the reactor and an identical in diameter, identical portion after the reactor where we only have inert particles. So if they are inert particles, so no reaction is obviously taking place in here as well as in here. So the reactants come at a temperature of T1 as they enter over here. This portion is perfectly insulated, as well as everywhere it's perfect insulation. So the reactants come at some temperature T1, and when they reach Z equals 0, the reaction starts. And as the reaction starts, if we assume it to be an exothermic reaction, so temperature will keep on increasing. And then it comes to this section where the reaction again stops, and the reactant mixtures go through these inert particles of same dimension and come out of this as product. So that's a very common arrangement in process industries, where a tubular reactor is preceded by a section and followed by another section where no reaction is taking place, and they are very well insulated. So the superficial velocity, this W is the mass flow rate, and this ρ1 is the density of the reactants corresponding to temperature T1. That means at the entry of this point. And there is some volumetric heat generation due to the reaction, which is denoted by SC, and which is non-zero only between Z equals 0 and Z equals L. In zone 1 and zone 3, the value of SC is equal to 0. What we have to do is we have to find out what could be the temperature profile in starting from zone 1 to zone 3. Zone 1, 2, and 3. So any speculation from your side, how would the temperature profile be in such a case? The reactants are coming at a constant temperature of T1. Nothing happens before it reaches Z equals 0. So at Z equals minus infinity, that means at a large distance, the reactants start coming in with T1. And this is at Z equals plus infinity. That means at a point far to the right of the end of the reaction zone, the products are collecting. The temperatures over here are, this is T1 and then T triple prime. So just your guess, what could be the temperature profile?
It might first reach to T1, then go up because of heat generation due to the reaction, and then again go down to T triple prime.
Someone, right? Someone, can you please repeat what you have made? There was some problem at my end. I didn't hear you properly. Can you please say it again?
If we assume that T prime or T1 is less than the temperature of the reactants, then it will start going
No,
towards T prime.
no, if I did not add this, the reactants are coming at T1. This is perfect insulation. So if you give it enough time, then at least over here the temperature is slowly will change to T1. So if you can state that, modify your statement again, once again. And this is a steady state problem that we are dealing with. You are on the right track. Can you restate your whatever you have understood?
So the inert particles will reach to T1 then, I think.
Right. And we are talking about temperature, talking about time where the temperature is quite large. After 10 hours of this process going, what could be the temperature profile? So what is your statement about zone 1?
The inert particles will reach to T1.
So everywhere the temperature is going to be equal to T1. So what you say is that T1 is equal to T prime.
Yes.
All the way up to Z equals 0. And then between Z equals 0 and Z equals L,
It will be more than T1 because there will be heat generation due
there
to
is some amount of
reaction.
heat generation. Yes, because of the exothermic nature of the reaction. And the profile is going to be, I mean, it may not be linear, it could be non-linear, but the temperature will increase in the region 2. How about T3? I mean, zone 3?
Then T triple prime will be equal to T whatever becomes of the temperature after heat generation.
So you're saying that T triple prime would be equal to whatever be the temperature over here. You can see the
Yes.
cards. So what you are saying is that T triple prime would be equal to whatever be the temperature at the interface.
Yes.
Okay. Any other comment or comments that anyone else would like to make? Okay, so let me, someone has made a statement, but we need to prove that mathematically. How far is he correct, or is there some modification to be made into his statement? So Raman, just one more time. If I need to draw a profile up to this, so this is my T prime. It could be a function of Z. What's going to happen after this? Is it going to continue and all the way up to this point? And then it's going to start increasing in some fashion and reach this point. And so can you connect this point, and how the temperature T3 will be here? Anyone? Just wild guesses. We have to mathematically solve it anyway. I was just trying to think intuitively how far we can go.
So
Yes.
from T prime to T double prime, it should be a horizontal line up to the interface.
Who's Adrija? Adrija, can you repeat once again? Are you talking about T double prime?
Yes, sir. The first part from zone 1 to zone 2, it should be a horizontal line.
From 1 to 2.
Yes, sir.
So you mean to say that this is going to be extended up to this point, and then it's going to start rising. So at Z equal to 0, if I increase, if I magnify this part, so this is Z equals 0, and it's going to be something like this, and then it's going to increase like this and reach Z equals L. So over here, this is the profile which you are suggesting. Am I correct in understanding you?
Yes, sir. Maybe that way.
Doesn't matter. We are all speculating right now. Unless we solve it, we won't be able to do this. And how about here at Z equals L? Anyone?
Sir, it should be horizontal line. Further.
It should be the horizontal line, like it's going to be like this, roughly in my drawing. So there's going to be a horizontal one like this. So from T1 T prime will be equal to T1 over here, and then it will continue all the way up to this point. Then it will start rising in some fashion, the one that we still yet to know. It reaches the second interface, and from that point, it's going to be a constant. That is what we have come across so far. Anyone having any other
Sir,
opinion?
I want to ask. Sir, I want to ask one thing. Hello?
Yes, can you repeat that? It's not very clear. Can you repeat that once again?
Sir, I want to ask one thing, that at z equal to 0, does there any diffusive conduction of heat
In which direction?
in
I'll repeat your question so that everyone is
back
on the same
direction? Yes, in back direction.
At Z equals 0, what he said is at Z equals 0, will there be any diffusive heat transfer? And then I asked him in which direction.
In the reverse direction of the
That means
reactant.
towards minus infinity.
Yeah.
So what you mean to say is that there could be a diffusive transfer of heat in this direction.
But if the slope at z equal to 0 is 0, then there will not be any diffusive. I mean,
No,
no
but there
transfer in that.
is always a flow in this direction. So do you think the diffusive whatever transfer that you are referring to will be there at Z equals 0?
No.
Let me just take your point and take it a bit further, and I would try to underline or underscore that this is a case where you have simultaneous conduction and convection. So what you have spoke about diffusion, you are referring to conduction, because diffusive heat transfer and conductive heat transfer are the same. So, but in this case, I have a convection and a diffusion taking place simultaneously. Plus, there is a region in which I have heat generation as well. The question that I would like to ask you is that, can you stop diffusion? When you talk about stopping the flow or reducing the velocity of the flow or bringing it to 0, you can stop convection. But can you stop diffusive heat transfer or conductive heat transfer? If you have a lump of sugar in your cup and you are stirring it, when you stir it, you're essentially creating a convective mass transfer environment such that the sugar crystal or lump of sugar dissolves more quickly. But if you take the spoon out of your cup, will the sugar melt or dissolve or not? It will obviously dissolve.
Yes, sir, through diffusive mass transfer.
Diffusive mass transfer. So the same way, and how can you stop diffusive mass transfer? Or when can you stop diffusive mass transfer?
So when the driving force is 0.
When would the driving force be 0, or what is the driving force?
Concentration difference.
Concentration gradient. So if I could make the concentration gradient disappear, only then I could stop stop the diffusive diffusive mass transfer. Project it to heat transfer. When can I stop diffusive heat transfer?
When temperature gradient is 0.
That means when the temperature on the zone 1 at the interface between zone 1 and zone 2, if the temperatures are equal. If the temperatures are equal between zone 1 and zone 2, then only I would be able to say that there is not going to be any diffusive heat transfer. So what is going to happen between here and here? First of all, two things we have to keep in mind, that it's one of the preconditions, one of the boundary conditions is that there is always going to be temperature continuity at any interface. If we are talking about a continuum dynamics, then there would always be a temperature continuity and a heat flux continuity at the interface. So let's try to, all this discussion essentially tell me something that it's not a problem as easy as we think. So what we have to do is, in the previous problem, in the previous photograph and picture, I'm going to take a slice of some length delta z and try to do a shell balance of energy over here and see what kind of a differential governing equation that I would get. So what I have once again is some delta z, and we know that there's going to be some flow of convective heat in convect. Did I do? Okay, so this is delta z, some flow of convection, some flow of convection out, some conduction out, and there may be some amount of heat which is generated in here. So in by conduction would simply be whatever be the heat flux in the z direction multiplied by whatever be the area through which it's the whatever be the cross-sectional area. And of course, the out would simply, what would be the expression for out? Area remains same. The QZ is only evaluated at Z plus delta Z. So this is in and this is out. Convection. So what is going to be the expression for convection? First of all, area should remain the same. And what is the convective heat transfer, convective energy coming in to this control volume? Your expression. What is the energy coming into the control volume by convection? You have a packet of fluid, and that packet of fluid is coming in there. What is the energy content of this? The same energy content is being added to the control volume over here. And what is going to be the end point of the packet which is going to cross the interface in 1 unit of time? What is this distance from here to here? How do you express this distance so that it gives you the amount of fluid which crosses this interface in 1 unit time? 1 second, let's say.
Flow rate.
Flow rate. Okay. But you are absolutely right. So if this is the area, then flow rate would definitely, what else should I write here in order to make it a flow rate?
velocity.
Velocity. So can you now tell me what is this distance? The distance from here to here? In 1 unit time, this has to be equal to V. If this is 25 meter per second, let's say, just an abnormally high value. So then the amount of fluid which is going to pass through this must be equal to the point where the furthest point that will cross in 1 unit of time has to be equal to 25. So this is, let's call it as this V1. And this, of course, is volumetric flow rate. So I multiply that with the local value of density to make it the mass flow rate. And what else should give me the energy? So this is essentially m dot. What else is to be added in here? Yes, please go ahead.
CP.
Right, and then
Temperature at that point.
or rather, you cannot express energy in absolute term. So this is some reference temperature across which all energy or energy calculations are to be made. And this is at Z. So T is the temperature, local temperature, and T naught is the reference temperature across which we are, which is the datum level for our energy calculation. And the one which is going, any question? Okay. If there are any questions, just stop me and ask me. So the one that goes out would simply be rho1 v1 t minus t naught, except this is evaluated at z plus delta z. So this is in and this is out. These are the in and out term by convection and conduction. And there would be rate produced, or rather the generation rate. What would be the expression for that? The volumetric rate.
Rate of reaction into volume.
And the volume would be pi r square times delta z. So this is your generation term. And now what we have is rate in minus out plus generation. These are at steady state, so they are going to be equal to 0. So the algebraic sum of in minus out for conduction, for convection, and the generation would be equal to 0. So once we divide both sides by this delta z, what we get is QZ, the conductive heat at Z plus delta Z, minus QZ evaluated at Z divided by delta Z, plus rho1 V1 Cp T at Z plus delta Z, minus T evaluated at Z divided by delta Z, is equal to SC, which is the volumetric heat generation. Then we, as we have done before, we are taking limit delta Z tends to 0, and over here is also like a, let's put a third bracket in here, so I do not have to write anything. And of course, then if I do that, then this becomes dQZ by dZ plus rho1 V1 Cp dt dz equals SC. That becomes my governing equation. The same way we have started our initial part of our momentum transfer course in fluid mechanics. So we wrote what are the in terms, we wrote what are the out terms, divide both sides by the smallest dimension. The obvious one, pi r square gets cancelled from all sides, but the delta z remains. We put the delta z in the denominator, take in the limit when delta z tends to 0, And from a difference equation, we obtain a differential equation, which is this. And of course, for QZ, but before we go into further solution, there is a serious problem in here, which we need to identify and which we need to appreciate. Anyone with some observation on some major approximation that we have made while doing this? What you see here is this control volume that we have drawn may contain the catalyst particles like that with some porosity in between. So when you take delta Z to tends to be 0, what are we referring? Are we referring to the region in which is going to consist only of the particle, or which is going to consist of an interstitial gap through which the fluid is flowing? Okay, so that is the problem when you do this limit delta Z tends to 0, when it becomes very thin. To our defense, what we are going to say is that we have to do this unless, because we are treating everything as continuum. So unless the system is within the continuum limit, all these equations are going to be meaningless. So what we are going to do, what we are going to assume when we solve this equation is that any temperature that you are going to get out of the solution of this governing equation is some average temperature which exists in that very thin layer when delta Z approaches to a very small number. So instead of this T being a point value of temperature, this is an average value of temperature at a given Z. So this limitation will have to be kept in mind. So this is some sort of an average temperature. All right. So we do this, and therefore I would write my K to be Z effective instead of the all these are effective values, d2t by dz squared plus rho 1 v1 cp. This is also some sort of an effective times dt dz to be equal to sc. And I'm going to do this for zone 1. I can write it for zone 2 and for 3. So what's going to be the equation in zone 1? This equation in zone 1, this is simply going to be minus kz effective, and I call it as d2t1 by dz square plus rho 1 v1 cp effective something dt by dz to be equal to, what should I write on the right hand side? Nothing takes place in zone 1, so there will be no heat generation. The zone 1 is filled up with inert particles, so therefore this is going to be 0. For zone 2, the SC is going to be some value, and for zone 3, this is going to be equal to 0. Okay? Any question? Now I have to think about what are the boundary conditions. At Z equals minus infinity, at Z equals 0, and at Z equals plus infinity. Okay. At Z equals minus infinity, if you go back to the figure over here, at Z equals minus infinity, T1 is going to be equal to T suffix 1. Okay. At the location between these two, T1 would be equal to T2. At this point, T2 would be equal to T3. And when we go all the way up to this, it is probably safe. It is definitely, you would see mathematically why it is important. You would see that Z equals plus infinity. I'm going to say T3 is finite. At z equals minus infinity, t prime is going to be equal to t1. At z equals 0, t1 would be equal to t2. And at z equal, I did not write z equals L. Your t2 would be equal to t3. So these are the continuity of temperature. The same way I have continuity of temperature, I also have the continuity of heat flux as well. So at z equals 0, I'm going to write K effective. I drop the effective just for convenience of writing, would be K dt double prime by dz. And for z equals L, same thing. So continuity of temperature and continuity of the heat, the thermal profile, the temperature, the continuity of the heat flux. How much time do we have? 2 minutes. You have a class after this? Please answer quickly.
No, sir.
I'll take, if you do not have a class, I'll take 3-4 minutes more to complete this. Is that okay with all those who are present? Anyone having any problem, please let me know. Okay, so I assume that you do not have a problem. So I'll, with your, I request you to be with me for few more minutes. So the temperature θ1, it's just a dimensionless temperature. If you solve it, it's going to be these B, C1, C2 are constant, which is obvious. This is a problem which you could see how it is solved in Bird-Stewart-Lightfoot. So I do not want to get into all the details. The conceptual part I am only going to discuss. And θ3, which is essentially T3, related to T3, is going to be C5 plus C6 e to the power Bz. Of these, I would bring your attention to this. Does it say anything to you about what is going to be the value of C5 or C6? θ3 is essentially T double prime, it's triple prime, dimensionless form. Can you say something about C5 or C6? Think and answer. For a large value of Z, what is going to happen to theta? θ3. In this, for a large value of Z, what is going to happen to θ3? Is it going to be large or small?
Small.
Pardon me?
It will be small.
It's e to the power Bz, and B is a positive number.
Then C6 should be 0.
C6 should be 0 as T3, that means essentially θ3 cannot be infinite. So C6 is 0. That means your θ3 is equal to C5. Okay. So I am drawing the profile right now. This is my zone 1. This is 2. And this is 3. So what is going to be the profile of 3? It's going to be like this. It is a constant equal to C5. But if you think about θ1, which is T1, how would it behave? it is going to be an increasing function of Z. And for realistically, this is what it would look like. This is how it would behave till the point it comes to the junction of 1 and 2. And in 2, it's going to increase and be like this. So since this is constant, therefore the gradient of the temperature T3 by Tz is 0. And if I go back to my previous one, since this gradient is 0, the continuity of heat flux demands that this gradient is also 0. So therefore, what you see in here is that not only the temperatures are going to be equal, since the gradients are equal, and since this gradient is 0 due to the constancy of T3, the gradient on this side should be 0 as well. Any question? We have seen that T3 to be equal to 0. If T3 is, T3 is a constant. So if T3 is a constant, dT3 dx or dz is 0. That's why it looks like this. And continuity of heat flux demands that dT2 dz is also 0 in such a case. So the temperature rises but asymptotically reaches the value of T3 at Z equals L or T2 at Z equals L, that means this point, with a 0 slope. So this is what the profile should look like. You can get a series of such profiles depending on the values of M3, C3, C4, M4, which would depend on the heat capacity, the flow rate, etc., that you could see in your Bart's-Note light in your textbook. I'm not going to spend any time on that. So that's going to be, the profile is going to look like this. Interestingly, over here, you could sense that because of the nature of the profile, the temperature increases as we approach the junction between 1 and 2. However, the slope at this point and the slope on the two sides of the interface should be the same, because dt1 by dz should be equal to dt2 by dz. The heat flux continuity. So what this exercise tells us is that for a perfectly insulated tubular reactor, you are going to get some amount of preheating as the reacting mixture approaches the reaction zone. But once it crosses the reaction zone, the temperature does not vary. So when you said initially that the diffusive heat flux, the convective heat flow is always from left to right, but the diffusive heat flow is dependent on the temperature gradient. If the temperature gradient is in the reverse direction, which it could very well be, because it only depends on the temperature in here and the temperature in zone 1. And we know that the temperature in zone 2 is going to be more because of the exothermic reaction taking place over there. So there will be a diffusive flow of heat in the reverse direction, which is responsible for the preheating of the reaction mixture. So in zone 1, there could be preheating, but when you reach zone 2, the temperature is going to remain a constant. There would be some flow of convection, but it's not going to give rise to a change. The reacting mixture go unchanged in terms of its energy content once it crosses and passes through this. So that's the important lesson which comes out through the thermal modeling of a tubular reactor consisting of a reaction zone, a preheating zone, and a recovery section in which we simply get the products at a constant temperature. And of course, depending on if it's a if it's an endothermic reaction, you simply get the same thing, but you are going to get a pre-cooling, so the temperature will drop. It will further drop, but then it will remain constant. So based on the exothermic or endothermic nature of the reaction, you may get a preheating or pre-cooling, but the temperature profile will remain constant throughout in this section. And the values of this C1, B, M3, M4, etc., as you could see, as you will see in your textbook, will dictate what is going to be the shape, and what kind of family of curves you would get for different values of M1, M3, etc. Any question? Okay, if there are no more questions, then what I would do is in the next class, I would introduce the equation of energy and solve problems which are of slightly different types than what I have covered. But the last problem that we have discussed essentially tells us so many complexities or so many interplays between different forms of energy transport are to be taken into account for solving a real life problem. Thank you once again, and we'll meet again at our next class.
Thank you, sir.